So before we end the final lecture, let's summarize what we have achieved in our measure theory exploration so far. So I'll base this summary on sort of our primary example that we've been focusing on. We started with this collection of intervals inside there, and there were like 4 types of intervals. It could be open, closed, or half open in both ways, or whatever. And this was a semi-algebra of sets on the unit interval. So it's a semi-algebra of sets. And then we defined lambda to be sort of sup minus inf, right? So it would take the interval a, b, for example, like this one, and then lambda of that would be b minus a. So that would be our notion of the length of an interval. So here we have, oh, and we also argued that this is additive, right? Additive and non-negative. I didn't prove it was additive in lecture, but you went through similar kinds of arguments on, I think, your homework 4. Maybe it was homework 4, where you did the rational version of this, where you only took rational points, but it was pretty much the same argument for why this lambda is additive. So you've got an additive non-negative function on a semi-algebra of sets. So there's a unique extension lambda bar extending lambda such that lambda bar, sorry, let me say that in a better order. First, let A be the algebra of sets on 0, 1 on the interval generated by the semi-algebra up here, also known as the collection of finite unions of intervals, also known as the collection of elementary sets, I think is what we called it. Then there's a unique additive extension, lambda bar, of lambda to A. That was proposition 1, 3, 10, that you can extend additively from a semi-algebra to an algebra. Then we wanted countable additivity for lambda bar, right? So we said let fancy K be the collection of finite unions of closed intervals inside the unit interval. Then we observe, hey, this is a compact class. K is a compact class. And also, it's an approximating class for lambda bar. So we had to make these 2 observations. And so therefore, lambda bar is countably additive. That was theorem 143. That if you have a compact approximating class for a non-negative additive function, then it's countably additive. Then, now finally, if you consider lambda bar star, the outer measure induced by lambda bar, that if you view, so outer measure is always defined on just arbitrary sets, but if we restrict it and consider it to only be defined on the collection of lambda bar measurable sets, so I guess I would use this notation for the collection of lambda bar measurable sets, then this is the unique countably additive extension of lambda bar to this. And if I consider it only on the sigma algebra generated by the elementary sets, then it's also the unique countably additive extension on that sigma algebra. So the sets in here, the sets in the lambda bar measurable sets, these are what are called Lebesgue measurable sets. And the outer measure induced by lambda bar here is called the Lebesgue measure. So that's, I think, a pretty good spot to end the quarter at, is we finally defined the Lebesgue measure. Now we defined it on the unit interval 0, 1, but we also have the tools to do this in higher dimensions because of those supplementary results from the notes that I added earlier. You can take sort of the product semi-algebra here and a product measure induced by lambda, and then run this whole thing basically just in Rn rather than in just R. Use for your compact class the so-called K-cells, that's what Rudin called them, the finite unions of products of closed intervals, and you can end up with the Lebesgue measure and the set of Lebesgue measurable sets on the unit n cube. So we end here with a defined Lebesgue measure, which we could have actually defined much earlier, but we wouldn't have known that it's countably additive, and it would have been hard to verify that it is well defined without all of this work. And we have this concept of Lebesgue measurable sets. So this is a pretty good start to your study of measure theory. If you want to continue, I think we have a pretty good start here. If you like the textbook that we used, then let me tell you that the plan I've been following is basically something he has here in the appendix on page 439, which is his plan for the order in which to go through sections. And I think it gives you a pretty good summary of what's very important to go through to get the fundamentals. So for example, if you want to continue on your own, I would recommend actually skipping 1.6 and maybe going to 1.7 and then going back to chapter 2. So it was his suggestion to do 2.1 earlier. So you can find this and view it as a suggested plan to proceed. Or if you didn't like this textbook, then find a different one, I guess. Yeah, so you can just ask me on Nectar if you want some textbook suggestions for continuing with this stuff.